Hello. I hope all of you are fine. Today we are going to discuss one important topic related to electrical and electronics engineering, that is harmonics. The term harmonics is very common in power systems as well as power electronics. Now, in this video, we are going to understand what is its importance, and apart from this, we will understand what is the meaning of harmonics and Fourier series, and we will do a simulation to understand these harmonics. So, before understanding about the harmonics, we have to understand what is Fourier series. So, the Fourier series is given by this expression where f of x is any periodic function, and I have the terms a naught, an, and bn. The value of these a naught, an, bn can be calculated using these equations. And what this equation states is any periodic function can be represented by a summation of by a combination of cosine terms and sine terms along with some DC value. This A naught, this term is called as the DC component of any periodic waveform. What is the meaning of this is, if I have a periodic waveform, that waveform can be split into n numbers of sinusoidal as well as cosine terms, and if you combine all these things, you are going to get the your periodic function. So we will understand these things using a simulation. These equations are there to represent a periodic function in the form of cosine and sine terms. Now we will understand the same thing using a simulation. So for that, I will use one simplest software, that is Psim. This Psim software is there. It is very user friendly compared to all other softwares. And here you have all these things. I am going to open one new file. So I have a new file. So here in this window, you can create any circuit. Required circuit can be created here. So I will use one sinusoidal AC source. You can see here I have a sinusoidal AC source connected. I will take a resistor. I am going to connect this resistor here. Okay. And I will make a circuit by connecting these two things. There is a sinusoidal voltage source and it is connected to a R load. Don't worry about this connection. We will see the waveform of this sinusoidal voltage. To have the voltage, to measure this voltage, I am going to connect a voltage probe. This voltage probe is connected here. You can see I have connected this voltage probe. This is connected here. Similarly, this is connected here. Okay. So you have options to enter these values. Okay. So I have the name of this voltage source. Let it be V1. I am going to have its peak amplitude, that is amplitude of this waveform, that is 110. Let it be 110. By clicking here, this will be displayed here. Okay. And instead of 60 hertz, I am going to make it 50 so that we can easily understand the things. Okay. So I have connected these things. So my circuit is ready now. Don't worry about this R value. Let it be a 10 ohm resistor, and I have connected this source to this R load. Now I am going to save this. Okay, I will save this one. I will save this one. Okay, and there is a thing here. I am going to run this simulation, and you are seeing a waveform. Okay, So this is showing only half portion. This can be the time of simulation can be increased using this sim control. I will make it up to 0.1 seconds. Okay, so now I will run the same thing and I am going to get this sinusoidal waveform. Okay, so you people got this one. What is the meaning of this? I have connected a sinusoidal voltage source here, so I am going to get a sinusoidal voltage source. This is simple and I hope it is understood. Now what we are going to do is I will connect another voltage source. Okay, so just see here, I have this one. I will copy this one. I will paste the here. Okay, 1 minute. Okay, so it is copied, it is pasted. Okay, so I will connect these two things. I am connecting them in series. Okay, so that means I am adding these two things, these two voltage sources. Okay, so let it be a 50 hertz. Okay, let it be a 50 hertz, and I am going to have some different magnitude here. Okay, so I will give 50 hertz. Okay, sorry, 50 volts. Let it be a 50 volts supply, and I have a frequency of 50 hertz, and I am going to get the combination of these two things. Okay, so I have a combination of these two things. Okay, so I will see what will be the nature of this voltage combination. Okay, so I will connect this one here. This is connected. Okay, I will save. Again I will run this one and you will see it is again a sinusoidal waveform. You can see its value here. In the previous case it was 100 hertz, but the peak amplitude was 100 hertz, but now this value is increased to 150. You can see here the value here is 150. Okay, so what you are observing here is the nature of this waveform is not changed. Okay, what is its nature? Again it is a sinusoidal waveform. Okay, so I have added two sinusoidal sources of same frequency, and the resultant is again a sinusoidal waveform. Now you can change its phase angle. Phase angle is also given. I am going to change it. I am going to shift this waveform by 30 degrees and I will check. Okay, so what happens to this combination? Okay, so you are seeing here some difference you are seeing. I will zoom this one. You can see there is a difference here. There is a difference. The waveform is changed, but nature of this waveform didn't change. It is again a sinusoidal waveform. Okay, so these things you must understand. I hope it is clear. Now what I will do is what happens if the frequency of it is changed. It means I am having a 50 hertz AC component or 50 hertz voltage source, and for that I am adding a 150 hertz voltage source. Okay, now I will make it 150 hertz. So what you will see will show here. Okay, so I am running this one. So this is my waveform. Okay, so this is my waveform. What happened now? You are observing that this nature of the waveform has changed now. It is not a sinusoidal waveform. And I will run it again to understand these things in a better way. I will connect another voltage sources here. So just a minute. Sorry. Just a minute. Okay. This is connected. Okay. I am going to make it this, let it be a B 50 hertz. It is the voltage across 50 hertz source. Similarly, I will connect another voltage probe. Where is that voltage probe? Or I can copy that also. Okay, sorry, this is connected here. I will delete. I will copy this one. Okay, I am copying. This is copied. Okay, so I will join these two things. Okay, I will call this as a 50. It was 50 and now it is 150 hertz. Okay, it is 150 hertz. Now I will connect another voltmeter for the resultant of these three things. Okay, this is control V. I will paste here. Okay, so I am going to measure this voltage across these 2 points, which is nothing but the resultant. Okay, so I will call this as a BR, which is nothing but the resultant. I will save this one. Again, I will run this one. Okay, so I will select all these three things: 50 hertz, 150 hertz, and resultant. Okay, so you can see here, you can see this waveform. So if you see here, this pointer, what is the value here? This green color, its value is shown here. Okay, so it is minus 49. Similarly, V50, that is 50 hertz, is 100, 108.58. Similarly, I have the resultant. Resultant is the sum of these two things. You can add these two things, you will get this value. In the similar way, at every instant, these two waveforms got added. Okay, so at every instant, these two 50 hertz and 150 hertz are added, and I am going to get this waveform. Okay, which is not a sinusoidal waveform. Okay, so this waveform I got, you can see. Okay, so here there is a phase shift here. Actually, it is having a phase shift. I am going to remove this phase shift for better understanding. I will make it 0, and I will make these two signals to be in sinusoid. Okay, to be in phase. Okay, so this is what you are going to get now. Okay, so there is a, this red color is going to represent a 50 hertz voltage source, and this green color is going to represent 150 hertz voltage source. Both these two things are added. Okay, and I am going to get this blue color waveform, which is a non-sinusoidal waveform. Okay, so what we conclude from uh, this simulation is, whatever this blue color waveform is there, it is periodic in nature. You can observe here, this kind of a thing is getting repeated after one cycle. Okay, so I call this as a periodic waveform. This is periodic in nature, and this waveform, this blue color waveform, can be split into two sinusoidal waveforms. One is a green waveform and another one is a red waveform. Okay, so this is what is called as a Fourier analysis. Fourier series is going to give us the sine and cosine components of a periodic function. Okay, and in the similar way, I have only added these two things. You can go on adding a 250 hertz, or you can also add cosine terms. Cosine terms are nothing but you have to shift this waveform by 90 degrees. Okay, so that will be called as a cosine term. Okay, so if you go on adding these things, any required periodic waveform can be obtained. Okay, any, you can obtain a square wave if you go on adding these kind of things: 150 hertz, 250 hertz, 300 hertz, 350 hertz. Like this, if you go on adding the things, you will see that this end is going to become flat. Okay, and I will get a square wave. In the similar way, by doing these kinds of things, any required periodic waveform such as sawtooth waveform, okay, or or triangular waveform, these can be obtained. Square wave can be obtained by proper combination of sine and cosine components. And this, if you see this blue color waveform here, which is the resultant waveform, it is going to have a frequency of 50 hertz. You can see here. Okay, one cycle is getting completed here, and this cycle is getting repeated again and again. So the time period of this resultant waveform is 20 milliseconds, which is nothing but 50 hertz. It is having a frequency of 50 hertz. And in this two waveforms, the red waveform, which is nothing but a 50 hertz, is also having the frequency same as this resultant. Okay, so this component, whatever this red color is there, this 50 hertz component is called as a fundamental. Okay, fundamental component. And this is called as a third, this is called as a harmonic. Okay, so it is called as a third order harmonic. Okay, which is having the 50 hertz, which is nothing but 3 times the 50 hertz. So it is called as a third harmonic component. Similarly, there will be a fifth harmonic, seventh harmonic, like that. So this red color is called as a fundamental component because it is having the frequency same as that of the resultant, and others are having a frequency higher than this fundamental component. So they are called as a harmonics. Okay, so this, in this analysis, this green color is a third harmonic. Similarly, I may have a fifth harmonic, seventh harmonic, ninth harmonic, like that. Okay, so this is one thing. So in, if you see this one here, I can, we understood about this cosine term and sine terms. Okay, so you can combine these things. You create one sine function, cosine function, add them, and you are going to get a different waveforms. And what about this one? This term is called as a DC component. So now what is this DC component? So we have seen this is a periodic function. Now to these two things, I will add some DC component. Okay, so our DC voltage source, and we will see how my waveform is going to change. Okay, so what happens here is I will connect a DC voltage source. Okay, let it be 100 volts. Don't worry about its value. Okay, so I will just connect these two things. Okay, I'm just adding these voltage sources. One DC is there, AC is there, and of different frequencies ACs are there. Okay, I will run this one. Okay. So what you are seeing here is this waveform is shifted. Okay, so if you properly observe this waveform, you can see here there is a shift here. Okay, so this is not starting from zero. Initially it was starting in the previous simulation, it was starting from zero, but now it is starting from 100 volts. Okay, so it is 100 volts. Okay, so the waveform has shifted. Okay, and you can see here, if you observe this waveform, okay, so it is unsymmetrical about a x-axis. 1 minute, sorry. You can see here it is unsymmetrical about x-axis. See here, this is the zero value. Okay, this waveform is having higher area in the positive side, whereas it is having a very small value in the negative side. Are you able to understand this one? Okay, so if you see this area here, this area is very small. Okay, but this is a positive area. Positive area is, which is very large compared to that of a negative area. It means this waveform is also going to have a DC component. Okay, so it is, whatever this blue color waveform is there, it is having a DC component along with 50 hertz component. Along with that, it is having a 150 hertz component. If I add all these three things together, I am going to get this waveform. Okay, so I hope this is understood. Okay, so in the similar way, you can use this software and you can go on adding the things, and you will get different kinds of a wave. So this is this is the real significance of Fourier series, and these harmonics Fourier series are commonly used in power electronics subject, where we are not going to get a pure DC, or we are not going to get neither pure DC nor sinusoidal waveform. Okay, so we will get some this kind of a waveform, or rectified output, or full wave rectified output, or the pulsating DC we are going to get. They can be split into the harmonics, which is nothing but the waveform is going to have a DC component, sinusoidal component, and cosine terms. Okay, so this is very important topic in case of power electronics subject. Similarly, if you observe these things, we have the odd wave symmetry and half wave symmetry. Okay, all these things are there. I am going to discuss about that in the next another video. Okay, so I hope it is understood. You can also download this software. It is freely available. Okay, demo version of this software is available. You can download that and practice these things. Thank you for watching this video. Thank you very much.